Hello, this is for Math 1101 and for the lecture period of February 8 and February 9. Although you can watch this at your leisure, certainly you should have it watched before your class on February 10 or 11. We're going to finish up 4.1, saving money, and go to 4.2, borrowing money, and kind of straddle the two sections, and we'll get going right away here. As I record this, the Super Bowl is coming up, so big day for football. Even though I don't care for either team, I'll still be watching. I have not missed a single Super Bowl. My father-in-law actually went to the very first Super Bowl. It wasn't even called a Super Bowl back then. It was in the LA Coliseum. So, anyway, I didn't go, but I've watched every game on television. So we'll be watching it. But let's pick up the math here. And we left off with this not so much used APY calculation. Yeah, I think there's a homework problem or two on it. I don't have much of a probability of putting it on the test, but I'm not going to completely zero it out. If I really run out of ideas, this is kind of on my B or C list, which I've done. The point is APR and APY are about the same right now. Low interest rates, APR is pretty much the same as APY, so it seems like I don't know about a waste of time, but it doesn't really move the needle much unless you have higher interest rates. So we covered this last time. We gave you an example where the annual percentage rate was considered to be 10%, but when you look at the average percentage yield, which is like an average of the time period that you have and what you're really getting if you just go straight to multiplying your balance by your number, then that's more accurately said is about 10.5%, 10.47%. We covered this. And we have one other example. I'm not going to pursue too much, but let's take a look at it. We're supposed to cover it. So back in 2014, a bank offered a 5-year CD at 1.09% APR. That sounds like ours. And if you buy a $100,000 CD, wow, great. Calculate a balance at maturity. So in decimal form, you have to move the decimal back 2 spots or simply divide by 100. That's the result. Don't really care about the leading zero. 0.0109. In terms of years, T is 5, and we use the APY balance formula. So we could actually go backwards to find the balance. And as I say, I don't have any homework on this. This is just sort of background information. This one will not be on the test, but just to show you very quickly, you add in 1 plus APY, so there it is, 1 and your 1.09%, raised to the 5th power. It's not a difficult formula, it just doesn't seem to have a ton of use. Now, this would give you a very accurate balance based on the APY. So just another way of looking at it, and you would go up $70.11. Remember, with money calculations, it's 2 decimal places. 2 decimal places every time. Used to have a problem that said round to the nearest dollar, but I've gotten rid of it. We will only have dollars and cents. So let's get into something else which is similar but a little different. We have present value, which is the amount we actually invest. Present value is just another word for principal. It's the same thing. But the idea is to tie present and future value together. This is just another way of saying it. So this is a good way of summarizing it, better than the first edition I taught out of. And the value of that investment at some specific time in the future is the balance after T periods. So we have basically the same formula as before, just rewritten. And I love the way they tied these together. Before they made them sound like they were radically different. Of course they're not. And the balance after T periods, as we've already seen before, was principal times 1 plus r to the t, a pretty fundamental compounding formula, and frankly not that hard. So instead of saying balance after T periods, you could say future value. Instead of saying principal, you could say present value. So this is a way of bringing the present value into the future. On a timeline, it's kind of going backwards. I'd rather go from left to right like a timeline would, or any kind of graphing method would, but this is just not the way they set it up. And it is an equation, so it really does not matter what side is which, as long as they're set equal to each other. So let's take a look at something like this. Basically, it's similar to before, but we're going to rearrange the formula slightly, and let's see what's up with this one. Example, you would like to have $10,000 to buy a car 3 years from now. How much would you have to invest now in a savings account that pays an APR of 9% compounded monthly? So this is a way of kind of refocusing the same structure. And incidentally, this happens again and again in Chapter 4. They talk about one way and they kind of shift gears and you kind of go backwards and see how the same structure can work. It looks a little different, but it's basically the same formula. It's like solving y equals mx plus b for x. There might not be much reason to do that, but it can be done. Just don't divide by 0, of course. Well, anyway, here we have monthly compounding. And there is a mistake, so it's part of the reason I'm here. Probably in the 3rd edition, they've corrected most of the mistakes. Anyway, R is equal to APR over N, and N is 12. And this is a very typical one, so N is 12. I've got to make sure this pen is on. Okay, so we take our 9%, which of course is 0.09, divide by 12, and you get 0.0075, 3/4 of an interest point per month. But we've got 3 years, so in terms of months, we multiply n times y, and so y times n, I guess you could say, and it's 36 payments, monthly payments over 3 years. So what they've done is they've rearranged the formula. They did have the 1 plus r to the t power times present value, and it wasn't there with the future value. Instead, they've got it in a situation where it's switched around. So we divide both sides by the 1 plus r to the t. I wish I had some animation to show you. So if we divide by this, then it cancels over here and reappears over there. So let me just rewrite it again because I kind of scribbled it out. So all they've done is they've divided both sides by 1 plus r to the t. And they have what looks like a new formula, but it's really the same thing. And why would they do this? They want to get the present value. To make this especially clearer than they've made it, we need to find what we need to do now to project into the future, because this $10,000 is future value. And what we need to know is now. That's the question mark. Now, it's going to be less than 10,000. I'll say that, because you're earning interest. So it's going to come up, which means your number has to be less than 10,000. So for somebody to say, oh, I need 15,000, no, that's not the point at all. The question is how much? So here's the deal. You take $10,000 and divide by your number, 1.0075. That's 1 plus r to the t. So 1 plus r, very easy. T is 36. No need for parentheses. Doesn't hurt, but you don't have to put them in here. But we would actually have to find out what that number is. Let me see what it is. Let me put an extra step in just for you. 1.0075 raised to the 36th power. That number is, and I will probably round this a little bit, 1.308645. 6 decimals might be enough, but if you insist, you can keep going and put down all the decimals if you wish. And there is a 1 over x key you could hit that divides it immediately, and then you could multiply by 10,000, and yes, indeed, you do get 76.4149 to the nearest penny. So it's really 489, but the 8 rounds up to a 9. So yeah, you got to have at least this amount. Now, does that mean you have to have it to the nearest penny? Not exactly, but if you have in the neighborhood of $7,640, $7,650, you'd be pretty much okay. You can make up the spare change out of your change purse if anybody ever carries one of them. I never did. Okay. Now we're interested in doubling time. And yes, we advertised logs. This is one of the 2 times that we will see logs. This is just a formula. We have people are interested in how long it takes their money to double or triple, which is just an easy extension of that, but we'll concentrate on doubling time. And so the number of periods to double is log of 2, which is a constant number. On my calculator, I type in 2 and find the log command. And this is a constant number. It doesn't get a lot of publicity like pi does or even e does. Turn my pen back on. Okay, did my battery die? Nope, it's on. Okay, so this number is 0.031029996. Well, there's all the decimals. Could probably round it out a little bit. Well, anyway, that's around 3/10, 0.3 is your answer. Now, R will depend on the interest rate. So you put it as a decimal, of course, and we'll give you an example of that right away. That's the only variable we have. You add 1 to it, take the log of it, and divide, and then you get the number of periods to double. Notice it does say periods. Be careful, because it might be years, might be months. You have to read the problem carefully. Now, if you don't want to break out the logs or even use a calculator in most cases, they have this time-honored, hundreds of years old approximation, which is generally very good. The book does talk about when it isn't very good, but I'll let you get the book. Everything except for Chapter 3, everybody should have. And then Chapter 3, you just have the slides, apparently. Still not sure about those with the printed copy. I haven't heard back from anybody yet. I think it sounds like most people are getting the ebook, which is fine, except Chapter 3, I guess. Approximate double time using the rule of 72. Here we put the APR as a percentage, and you leave it alone. I'll just pick one off the top of my head. Say your APR is 2%. that sounds about right. So in this particular case, we'll just use the 2, and then we get kind of a not very pleasant answer. 36 years. And this will be definitely in terms of years, because this is an annual percentage rate. They should have said that. So this is in terms of years, and we'll put that down right here. Whereas over here, it's a little bit more flexible. It has to do with periods, which might be months, so you have to be careful about that one. But notice this is an approximation. Let's say we have an APR of 8%. I can't remember what example we're coming up with, but then we would have 72 over simply 8. Do not put a decimal in. This is a rare one. But then you'd have only 9 years. Now, I'd rather have to wait only 9 years for my money to double as compared to 36 years. So in other words, with today's interest rates, your money will take a whole lot longer to double. Now, I have to admit, this assumes a fixed or basically an averaged interest rate. An average would change a little bit, but we don't need to break out calculus for that kind of stuff right now, or ever in this class. So, if we have 8% over the next, say, 9 or 10 years, we can expect the money to double in only 9 years. That's the power of the interest rate. The APR, which is the one I'd like to concentrate on. So let's move over to an example of this, and yeah, this is exactly the same one I just did. I guess I'm clairvoyant or something. Suppose an account has an APR of 8% compounded quarterly. Oh, now this is a little different. So estimate the doubling time using the rule of 72. Calculate the exact doubling time. So the rule of 72 is a quick and dirty approximation. Notice a lot of numbers divide into 72, and a lot of them you can do in your head. I hope, anyway. And if you can't, go ahead and use a calculator. But the idea is to come up with a quick, good approximation. That's the whole idea of estimation, which is what that little supplement is that suddenly showed up in our classes. It's in front of the homepage, which I do not care for. If I can fix that, I will. And I don't know where it came from. Nobody sent me any kind of email. I know there was some discussion last semester about including some materials. This must be the follow-up to that. I just wish it could have been put somewhere inside the homepage. Maybe I can figure that out. But some of them require a password. I do not have the password, so just ignore those. But if you look around for like the PDF quote-unquote book, you can find some nuggets of information in there about estimation and number sense, powers of 10, stuff like that. It's just meant to be optional supplemental material. I think the A student will check it out just to read a little bit more, but that's entirely up to you because nobody told me about it. I can't exactly require it, but it's not bad. Okay, anyway, this APR, the rule of 72 doesn't care about months. It's always going to be in years. So that's one slight advantage. Plus, since so many numbers divide into 72, it's generally pretty fast. Assuming it's like a whole number APR. I'm not going to talk about 8.33 or something like that. Then you really do have to use a calculator. Okay, now that's the estimate. The exact doubling time, which is what you might really need, involves the calculation, and this time especially when it's quarterly, we do have to pay attention to it. And if n is equal to 4, we divide by 4 and get 2% per period. Per period. That looks almost the same. Per period. And the period is quarterly. So then what we have to do is change our r. Can't use 0.08, you have to use 0.02. And then when we get log of 2, which is about 0.301, and divided by log of 1.02. So I type in 1.02, at least on my TI-30XA calculator, and we have to discover how your calculator works. You have to do that. Tutoring Center is really good for that. We've got 3 different tutoring links in your syllabus. Please use them. Anyway, that number, when you take log of 1.02, as I round it severely, like to only like 5 decimal places, that's 0.00860, and then that number will turn into be 35 periods, 35 quarters. So let me say it's 35 quarters. So if you had 35 quarters of money sitting on a desk, that would, as you divide by 4, be 8 3/4 years. Or, if you'd like to convert to months, which is perfectly okay, 9 months, because of course 3/4 of 12, very easy to see, that's 9 months. So I wouldn't care. If you said 8.75 years, I'd take it. But keep in mind, sometimes you have multiple choice questions where that may not be available, so you may need a little bit of flexibility for things like this to convert some fraction of a year into months. However, we would never go beyond months. I've seen it done for months, days, and then hours, minutes, seconds, and decimal part of a second. We don't need to go that deep, but it's possible you may need to go to months. So keep that in mind. So anyway, let's move on and go to number 8. With an installment loan, and now we've turned the page and gone to 4.2. So this is the new section, and well, not as fun a topic, but it is a necessary part of life, unless of course you're independently wealthy. And then you may not need to know too much about this, but even those type of people would know about it because they have lots of business associates that deal with it. With an installment loan, which is a very general term, you borrow money for a fixed amount of time called the term of the loan, and you make regular payments, usually monthly. That's all we'll concentrate on. So 4.1 is open-ended as far as the time period. 4.2 will stay monthly, I believe, every single time. Anyway, to pay off that loan plus interest, because they're going to get their interest accumulated during that time. And it's not simple interest either. They'll never want the simple interest. They always want the maximum pay, which is compounded. That's just the deal nowadays. Back in the 1700s, it might have been different. Well, anyway, the amount of payment depends on 3 things. The amount of money we borrow, the interest rate, and then, of course, the term, the time period of the loan. So those are 3 periods. Well, that's nothing new. That's the same as earning money. But we're now going in the other direction, and now we're talking formulas. So this is why I've been talking about this kind of thing and all the layers of parentheses and stuff. What I tend to do is when I write this stuff down, when I am live in person, I just call this MP for monthly payment. And amount borrowed, I just call it AB, just to quickly summarize it. But you have to be very careful because the parentheses matter a lot, and including Excel, if you miss a parentheses, you're done. Either it gives you error or it gives you the wrong answer, which is probably worse, especially if it happened to be close and you couldn't really tell. Obviously, if you get an answer in the trillions or answer in the pennies or some sort of negative number, you're wrong. But if it's a reasonable number, then maybe you got a good chance of being right. So anyway, it's amount borrowed times R times 1 plus R to the T, which we've seen before. And then we take that 1 plus R to the T and subtract 1. And divide by it. Now, technically speaking, these bottom parentheses are not necessary. You could delete them in the formula. But when it comes to Excel, you'd better keep them because otherwise we don't know what we're dividing by. Now we replace n by 12 every single time in 4.2, that is. And anytime you're borrowing, oops, I didn't mean to do that. And of course, we need a decimal. The only exception that I remember is the rule of 72. You do not put that one as a decimal. You have to just leave that one alone because it's meant to be a quick 10-second mental calculation. And it's meant to be pretty close, by the way. And oh, but I didn't bring up the point that when we had the 9 years versus 8 3/4 years, I should have said that, yeah, look how close that was. It was off by 3 months, but relatively close for a lot less work in many cases. So 8 3/4 years, 9 years, not too bad an approximation. And most of the time that Rule 72 works pretty well. So when I ask questions like that, I typically ask for both. And so keep that in mind, that one's typically easier than the other. And anyway, here's an example. You need to borrow $5,000 so you can attend college next fall. You get the loan at APR of 6% to be paid off monthly over 3 years. Calculate the monthly payment. What's the total of the payments? How much interest is paid and all. Let's do these one at a time. Can't just bite off too much at once. Okay, so if we can calculate the monthly payment, that's what this formula is for. Let's take a close look at it. And this is one of those cases where the exponent isn't too large, so I would give you permission to round to 5 or 6 decimal places. 5 is pushing it a little. 6 will generally be fine. So if I see, especially if I see your work, and I see you put down 6 decimals, and then if you're off by, you won't be off by more than a few pennies, and you will not lose any credit at all. But if you start to cut it back to 4, 3, 2 decimal places, it's laughable. You could get lucky. It's possible, but it could be way, way off. Could be off by hundreds of dollars. Do you really want to take a chance on that? Probably not. Anyway, let's take a look at the answer. And we, of course, divide our 6%, 0.06, by 12. It's 0.5% each, 0.005. And we want to pay it off in 3 years, so we have the very standard 36 monthly payments. Very easy one. Many car payments are done in 36 months. I did that one time. Okay, so break out our formula using the full-on English words. The monthly payment will equal something in terms of the amount borrowed. We multiply by this factor, and we divide by this factor. That 1 plus r to the t is a recurring thing. We see it in so many formulas. May as well just get used to it. And so we plug in the numbers. The amount borrowed was 5,000, and our r for months, of course, is only 0.005. Then we'll have to multiply that. They could have put another x in here. They could have just put dots in too. I don't know why they didn't. Take your 1 plus r, 1.005. Just adding 1 is easy. And raise it to the 36th power, and then that's your numerator, and divide by that same number, 1.005 to the 36th power minus 1. Let me show you some details. I typically just bundle the first two numbers right off the top because it's just easy. It doesn't really mean very much, but it is a way of getting going that anybody could do. So as I try to show some work here, those two numbers would be 250. 1.005 to the 36, let me just put a dot here instead of an x. So I'll type in my 1.005, raise it to the 36th power, and I'm just going to round it to 6 decimal places because this one is not a really long loan. But please keep in mind, it never hurts to put more decimals down. More decimals, the better. And then 0.5, I'll just call that a 1. So that's that factor that came from that calculation there. Now here's the thing. Once we've got this number, all we have to do is keep it and subtract 1. So what I'm going to do is I'm going to use that leading 0 just to make a point, even though I don't usually use it. And I can just copy the decimals down. That's actually not so bad. So, you know, even if you despise formulas or you have nightmares about them, well, if you learn some of the tricks and you really don't like Excel, then at least you have another choice. So anyway, I've got the number in my calculator. I'll just go ahead and use it. Multiply by 250 and the 1.1966, etc. Then I have to keep that together. It's around 299, by the way. You could show that work. And I'll divide now by 0.196681, and I get a value of $15.21 Actually, because I shifted the decimal over, I'm sorry. That's going to be $152, and I got 9 cents. So as you see, I missed it by 2 cents. I'm wrong. Should have used more decimals. See what I mean? The only way to get it, well, not the only way, but a major way of getting it exactly right is to use all the decimals your calculator will give you. And even then, there's one case coming up where the best you can do isn't good enough. That's where Excel would actually be the victor there. But as I say, 2 cents, I'm not worried about 2 cents. A couple $100, oh yeah, I'm worried about that. So let's put it in perspective, in other words. Okay. So our payments are $152.11. Now, yeah, there's a little bit of round off on that, but we will ignore that. That's not considered significant, even over 360 months for a 30-year payment plan for a mortgage. Sometimes, though, companies will put an overage or an underage in the last payment to make up the difference, and it's usually just a small amount. In fact, I think often that's what happens. So anyway, we multiply by 36 months, we have a grand total payment of $5,475.96. This was part 2 of the follow-up problem. We already answered the main problem. The payment is $152.11. 36 of those payments were up to almost $5,500. And then the final question was how much interest was paid in all. Well, we borrowed $5,000, and we're paying back more than that. Surprise. Hope nobody's surprised by this, because that's just the way loans work, unless, of course, it's from a family member with 0% interest. That's different. That's fine. Not much calculation needed there. Okay, so we subtract the two numbers, and we find that they have paid this much in interest, 475 and change, 476, I guess, in interest. And so you have to think about it. Over a 3-year period, it's worth going on an extra $500 to get this loan. Okay, that's the way it is. And by the way, this is very typical. Only 6% interest. They came out kind of lucky. Credit cards are at least 18% most of the time. And anyway, I haven't been shopping around for things like that recently, but that may change. Suppose you can afford a certain monthly payment. How much can you borrow to stay within that budget? Okay, let's compare the formulas as I go back here. We had monthly payment on the left side and amount borrowed on the right side. Suddenly, we've switched gears. The amount borrowed is on the left side. My pen keeps dying on me. And so they switched positions. And I'm not going to take the time to explain it algebraically, but it turns out these have traded places as well. We've just taken the inverse of a formula. So if y equals 1/2 x, x equals 2y. That's an inverse as well. That's a very simple one. Where they just traded places. Yes, these formulas are about the same. They're just emphasizing something else. This time we already know the monthly payment, but we want to see what we can get with it. That's different than before. Before we had it the other way around. We wanted to see what the monthly payment would be because there was already a fixed price on the thing. This time, it's not a fixed price. We have a fixed monthly payment. We'd like to see what we can get for it. So, anyway, notice they put the extra long formula in here. I'm not a fan of that, and I'm afraid our formula sheet may emphasize those types of formulas. I'm not thrilled about it, but it is a department sheet, so I'm hesitant to change their requirements. But I do want to point out that you do want to get your R right away. You want to get your T right away. Normally that's n times y, but 12 times y here because n is always 12 in 4.2 and 4.4 as well. Those sections, so you get so many 12s, be careful because we may get some 4s to you. I'll stay away from all the 365s, if you know what I mean, the daily calculations. I don't want to do those. Those are tedious for you and for me. I'd rather stay away from them. There probably is some homework on the daily calculations, so definitely try it. I really don't have much of a plan to do 365, but of course, if we come up with a common final, which is always a possibility, I could get overruled, so, you know. It didn't happen last time, but it has happened in years past. In fact, it was standard practice in years past, so I can't swear to anything, so don't take me to court over promises I make in these lectures. If I get overruled, I get overruled. But meanwhile, it's the same stuff. R, 1 plus r to the t, so this is all the same thing, but it looks a whole lot worse. I'd rather not use this. Get your R, get your t done in advance, please. Smart students do that. Unless you just love working with complicated formulas, I don't know why anybody would. It just slows you down. You get stuck. You make more mistakes. I've seen so many people try the long formula. It's just so disgusting to me. So use the shortcut formula. Be sure you get your R and your T done first. I can't overemphasize that enough. Meanwhile, let's try to work with this formula. This is a little bit of a glitch here. I'm not sure where that came from. So we're going to buy a car, and we can afford to make payments of $250 a month. For 3 years. Okay, 3 years is popular, and APR is 5%. Okay, so for what price automobile could we be shopping for? what can we buy for $250 a month for 3 years? Well, you could simply take 250 times the 36 months. What would that be? I'm curious. This is just a hypothetical, and man, this would sure be easier, wouldn't it? 250 times 36 is 9,000. So you'd say, oh, I can buy a $9,000 car, but the problem is there's interest involved, and you've lost some of that 9,000. Now you're down to, of course, looking at the bottom line, about $8,300 of automobile, because around $600, $700 is going to interest. Sorry. Just the way the world works, I guess. And so anyway, the point is you put your $250 in. This time R was not so friendly. That is, APR was not so friendly. Remember, R is APR over N. And in this particular case, it's 12. 5 over 12 isn't all that friendly, sorry to say. In fact, let's put this into decimal. So that will be 0.05. Let's divide that by 12. I'll use my calculator instead of making a mistake. And that's going to be about 0.0041, and then several decimals. I pledged just around to 6 decimals, so I will just round this to 0.004167, and it shouldn't make very much difference. Now, I'm not sure if I'm going to take the time to go through this entire calculation. Maybe I can do that during some of the reviews for the test coming up not too long from now. But the point is you would have all that stuff. Let me see if I can write out part of it. You'd have 250, of course, and you'd have 1.004167 rounded to the 36th power. Subtract 1. Notice the 1 is upstairs. And subtract the 1 is now upstairs, not downstairs like before. Everything's kind of backwards and upside down. Now we have our 0.05 over 12, which is just your basic 0.004167. And that's going to be multiplied by this number here. But the trouble is, it's the same as this. Not trouble at all. It's actually a fortunate coincidence. We just don't subtract 1 this time. So that's going to be our 1.004167 to the 36th without subtracting 1. Oh, what is that number? Even though it's a rounded number. Well, actually, I have all the numbers in my calculator, so I think I'll just leave it alone. And I'll raise that to the 36th power. I guess I will run through this calculation. And so we have equal to 250. And that number I just got on my calculator is 1.16147. I'm going to subtract 1 right now. Why don't I just do it right this? I'll do it this way. The complicated number's down below, so let me write it down right now. 1.16147, just rounded to 6 decimal places. There it is. If I subtract 1, it's the same number, except it's got a 0 in front. So 0.161472, a near duplication, not quite. These numbers are all rounded. We're inviting certain issues to show up, but that would be what we get. I'm going to see what I happen to get here. I've got the number in the numerator already in my calculator, even though it's got more decimals, so I'm being a little bit inconsistent on it. Multiply by 250, you get about 290 upstairs. Divide by 0.004167, and then continue to divide by 1.161472, and I'm getting a number that's not really that close, so I've made a mistake. But I'm convinced that I'd be within a few pennies of the actual answer, and that will be acceptable if you're using the algebraic method. Now with Excel, if you type it in correctly, you shouldn't have to really worry about round-off error. That should be almost never a problem with Excel. That's one big advantage of Excel. Suppose we need to borrow $15,000 at an APR of 9% to buy a new car. This is a little glitch here. 3.5 years is supposed to go here, so I'll put that in right there, cross that part out. Okay, so what's the monthly payment? We're going to do it 2 different ways. If we borrow the money for 3.5 years, and we had 15,000 and 9% and all that, and we'll go to part 2 a little bit later. So let's go to part 1. R is the monthly rate. We got 9%, 0.09, divide by 12, 0.0075. Now we have a rare half-year situation. So use 3.5, multiply by 12, and we have a kind of a non-standard payment that you'd have to make a special deal to get. Not impossible, but certainly a lot of them frown on it. 42 months. Nothing wrong with it mathematically. You could pick almost any number for that. But anyway, we have our monthly payment formula. the one that gets you monthly payment. We want to see what our payment would be. So we put in the amount borrowed, $15,000, and put in the R, put in the 1 plus R to the 42 power. This time I'm not going to show you all the details. And then down below, 1.0057. Notice we have to add 1 each time. So these numbers are the same. The only difference is this time we have to subtract 1 from the bottom line. You should get very close to $417.67 for your monthly payment. And if you round, you should probably expect to be off a little bit. And frankly, on a multiple choice problem, I've seen teachers put multiple choice answers that are all within a few pennies of each other. That's pretty mean-spirited, in my opinion. I remember tutoring those people, and they were not happy because you had to get it right to the X decimal place, 6 decimal place, or something crazy like that. And I do not plan to do it. My answers, if they are multiple choice questions, which some of them will be, they will be spread out far enough you'll probably be able to guesstimate it, even if you didn't hit it right on a bullseye. Part 2, though, what did Part 2 have to say? We find we cannot afford a $15,000 car, sad to say. We can only afford a monthly payment of $300 instead of $417. So what price car could we get for the same stuff? 9% APR, 3.5 years. Okay, what would happen? Well, let's find out. The monthly interest rate, same, 0.0075, still 42 months. All that part's exactly the same. And so we put the numbers in carefully, but notice this is the amount borrowed formula. This one locks down the monthly payment of $300. This is backwards from before. Just same structured formula, it's just going in another direction. So, some of the numbers will be exactly the same as we already calculated. So we just kind of fill in the blanks. I guess I have a minute. Let's go ahead and pick some of these numbers. 1 plus R to the T, 1.0075 as I try to underline it. My pen will wake up. Raise that to the 42 power. Let's just see what that is. 1.0075. Y to the X, 42, equals, and that's about a 1.36, etc. So let me put down some numbers. 300. I just said it was 1.36. I'm going to subtract 1 right now and call that 0.368649. Actually, that does round up to a 5.0 in 6 decimal place world, which I'm going to use. Because this is only 42 months. It's not a great deal of time. Our R is super easy. Just copy it down. Don't need the leading 0 if you don't want it. And then we multiply by the number with the 1, because we didn't subtract 1 from this. I did this in the formula order this time. That's going to be 1.368650. The 0, I guess you don't have to write down. And this number had to subtract the 1. This number did not. But notice all the decimals are the same, even if you include 9 or 10 decimals. Okay, so let me see what I can get as I type this in and see how accurate we are. 300 times 0.36865. Then divide by 0.0075 and then immediately divide by 1.36865. I get the number off by 1 penny. 10,774 and 12 cents. All right. Not the end of the world. Full credit would be given, of course. So, but you have to give me at least 5 or 6 decimal places for me to consider that. If you only give me less, then, of course, the credit will come off further. So you can shop for a car that costs no more than this amount. In the real world, that would be probably rounded to the nearest 100 or so. You'd have to keep it about $10,800. You could make up the difference in spare change found on your couch or something like that when people used to use change. Well, anyway, that's the plan. So $15,000 car, not going to happen, but maybe something a little less than $11,000 might happen. So that's the idea. And that's how our formulas get used. So that's going to be it for this particular lecture. We will continue live on Wednesday, Thursday of next week. That's going to be February 10 or 11. In fact, for the Monday, Wednesday crowd, we have a holiday on the 15th. No recorded lectures next weekend, or early next week. For the Tuesday, Thursday crowd, we will have 3 live lectures in a row. We're going to be going a little bit slower than the Monday, Wednesday people, which will have to go a little faster to catch up because we need to get on the same page ASAP. So that's just the way it is, and I will not take the time to record a lecture for next weekend. Tuesday, Thursday people will be live 3 times in a row starting next Thursday, whereas the Monday, Wednesday crowd will have a holiday, but we'll have to go just a little faster to get caught up. So try to pace it so it's not super fast or super slow. We'll just work it out to balance it out. But holidays, I've run into this before. As I already mentioned, I was off by 3 days last time. It was awful. So this time, not so bad, and we'll make up the difference. Anyway, I hope that whoever team you wanted won the Super Bowl. If you're seeing this after that, or if you don't even care, that's fine too. Maybe there's a Puppy Bowl on instead. So anyway, have a nice time, and we'll talk to you live Wednesday or Thursday of next week, the 10th or the 11th. Email if you have any concerns, and we'll talk to you later. Bye-bye.